Let's look at sphere packing. For centuries, mathematicians have been curious about the optimal way to fill space using identical spheres. For example, in 2 dimensions, the question was, how can we arrange pennies on a table such that they are as dense as possible? And it turns out the best arrangement takes up about 91% of the space. For spheres, it was much harder, but we found the optimal arrangement takes up about 74% of the space. Now, for most dimensions higher than 3, we know very little about the best way to arrange spheres. However, as we go from dimensions 3 to 4 to 5 and so on, the gaps between the spheres start to increase from the 3D case. But for some reason in dimension 8 there are new gaps that are just large enough to hold spheres that can be perfectly locked into place, resulting in that optimal arrangement which takes up about 25% of the 8-dimensional space. So we do know the math in 8 dimensions, and guess what? The math of optimal sphere packing was determined in 24 dimensions as well, just like the kissing number problem. By the way, for anyone saying what's the point of this, it turns out sphere packing and the hypercube graph have applications in information encoding theory when it comes to correcting errors in data that show up in noisy communication channels. For example, let's say if I want to transmit the word yes to someone, I'll send them a 1, and if I want to transmit a no, I'll send a 0. Now this is simple enough, but errors could come up when it comes to long-distance communication. So instead, I'll send 3 1s for a yes and 3 0s for a no. That way if an error does occur, like in a message that says 101, you can still say that's more likely to be a yes since 2 of the bits are a 1. Well, we can think of each possible message as a point in 3D space located on the corners of a cube. We'll put a sphere centered at the 111 message and one at the 000 message. If the radius of those spheres matches the length of the cube, then whatever messages they cover will be interpreted as the message at the sphere's center. Like here, the 101 message would be interpreted as the 111, or yes, since that sphere includes both of those corners. But if I want to include more words than just yes or no, I need to pack more spheres into the space. Yes, this example is pretty simplistic, but hopefully it shows how packing spheres tightly into space does have direct applications. And as we add more bits, we do the analysis on higher dimensional hypercube graphs, meaning we're dealing with higher dimensional sphere packing. Now let's see something weird in 9 and 10 dimensions. Imagine a square that is cut into 4 smaller squares, and then draw a unit circle in each one of those as shown. Then draw another circle in the center that is tangent to the 4 others. You'll notice that center circle is pretty small relative to the entire square and is far from the edges. We'll do the same thing in 3 dimensions, which would involve a cube being cut into 8 pieces, and those each being filled with a unit sphere. Then we'd pack a sphere in the very middle such that it barely touches the other 8. Here you'll also notice that the sphere is much smaller than the cube. But as the dimensions go up, that central sphere gets larger and larger, and in 9 dimensions that central sphere actually touches the edge of the 9-dimensional cube. Then in 10 dimensions it breaks through the sides of the cube, even though the cube, well, looks like it should be the boundary of the inner sphere holding it inside. However, when the sphere breaks through the cube, it still has a smaller volume than the cube. That is until dimension 262. After 262 dimensions, the hypersphere becomes larger than the hypercube, volume-wise. Okay, don't officially quote me on that, as I found it in various forum posts rather than an official source, but once I came across that information, I really couldn't exclude it. Now let's look at an example that's kind of similar to the sphere packing we saw earlier. Let's say we have a bunch of oranges, or spheres, that we need to wrap using